Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Thank you for joining the GeoScience and GeoEnergy webinar of 17th of September 2020 today. It's our pleasure with Singh from Heriot-Watt representing Sebastian, who couldn't attend. He's giving actually a talk at the same time somewhere else. And myself from TU Delft to host you again with yet another talk this week. Please do subscribe to the channel. We have more than 1,200 subscribers. It would allow you easily access the previous talks as well as getting notification for the upcoming or any live event you might have missed. And also, Kamal is involved with other colleagues in Tea Time Talk series. You have seen him in other channel as well. So please do subscribe, attend, especially junior researchers. It allows you volunteer to give presentation about your research, at the same time learn about a diverse topic of the porous media and geoscience related subjects. Without further ado, I would like to introduce our speaker, our keynote speaker of this week. It's my pleasure and honor to have Professor Behnam Jafarpour with us. Thank you very much, Behnam, for accepting our invitation and being here quite early in the morning in California. Behnam, I'm gonna just introduce him briefly to you, and you can easily just Google him. You will see how cool and how groundbreaking works he has done in the field of geosciences and engineering. Behnam is professor of chemical engineering and material science with joint appointments in electrical and computer engineering and civil and environmental engineering departments at the University of Southern California, USC, and the School of Viterbi School of Engineering. He earned his PhD and master degrees both from MIT. His PhD was in civil and environmental engineering, and his master's in electrical engineering and computer sciences, both at MIT. In 2008, he graduated there. And then he moved to the University of Southern California, USC, where he is today. His research lab, Subsurface Energy and Environmental Systems, SEES, is where he is leading the research there. This research lab focuses on developing low-rank representations, inverse models, and optimization techniques for characterization and control of complex subsurface flow systems. He's co-director of the USC Energy Simulation Center for Advanced Reservoir Characterization and Forecasting, ARCF. His groundbreaking work, publications, and impact in the society is known to many of us. I would like to ask that all the audience, please go and visit his Google Scholar page and other portals where you can find his phenomenal work. And today, we are pleased to have him here with us. He's going to give a presentation about low-rank representation of the subsurface flow inverse problems. Please note to the audience, Behnam's lecture will last for about 30 minutes, followed by questions and discussions. And like before, please type in your questions in the chat room, the chat box, and Kamal will chair the discussion session after Behnam's lecture. And do not wait until the end of the talk to post your questions. Do feel most welcome to post them whenever appropriate, because those questions earlier posted might also trigger other questions as well by the other public audience. Without further ado, I would like to welcome again Behnam and give the floor, the screen, the bandwidth all to him. And thanks once more, Behnam, for graciously accepting our invitation. The stage is yours.
Okay, thank you, Hadi and Kamal, for having me today. And I would like to start by thanking everyone for joining in. I hope you're well and safe everywhere you are. And I'm going to talk about low-rank representations for subsurface flow inverse problems. Basically, some perspective on low-rank representation from Fourier and Wavelet, the classical techniques in image compression, and to what in recent years have become an important topic deep learning application to subsurface flow inverse problems. So let me start my presentation. So a brief overview of my presentation today. I'll first briefly talk about subsurface flow inverse problems. Most of you are familiar with these type of problems, but I will just give a short overview of some of the challenges in inverse problems that we deal with in subsurface environment. Then I will switch to low rank representation, the motivation for it, and mainly look at compressive transforms that are ideas borrowed from signal processing and approximation theory. And the third part of my talk is related to deep learning and neural network architectures and how they can be used for low rank representation. And lastly, some overview of implementing inverse mapping through learning in low-dimensional manifolds. So let's start with the first part. The reason we are interested in subsurface flow is because of significant impact of the underlying resources that we have in the subsurface environment, from groundwater, environmental aspects related to subsurface, all the way to energy, conventional, unconventional, as well as renewable. And the key characteristics or the key commonality in all of these problems is the need to understand the flow and transport in these systems and to be able to predict their behavior and to be able to make a better decision in terms of their development of the resources and cleanup efforts in case of contamination. Now, if you look at understanding the flow and transport, there's a rich literature on simulating flow and transport in subsurface media or porous media. And the idea in doing so is generating a computer model that would represent the actual physical environment and trying to predict the expected behavior based on some underlying physics of these kind of systems with some input from us as people who are developing these resources and basically some responses that we observe. In general, there are two sources of errors and uncertainty that we have in doing this kind of modeling. The first is related to the description of these systems, material properties, and some of the parameters that are input parameters into these reservoir models. And the second source is related to the description of the dynamics and the physical processes that take place. So there's been a lot of progress made in improving these inputs and into the simulation effort, including representation of the physics as well as the description of the properties of the subsurface environment. By looking at various sources of observation and also gaining a better understanding both from experimental work and theoretical work that people have done. Now, when we look at these kind of flow simulations, there are obviously the forward problem where you construct a simulation model and you use that in order to predict what will happen in these systems, the dynamical states and their evolution in time and space, and from there predicting the responses at the observable locations, in particular wells that we drill into the system. So that is typically referred to as a forward problem, where you solve flow equations in order to predict the behavior of the system. The inverse problem, which is what the topic of today is related to trying to improve our description of the reservoir properties, subsurface properties, based on the responses that we observe, the dynamic responses that we observe from this system. And both forward and inverse problem have been the subject of significant research and progress in the past few decades. So some of the challenges from this point on, I will focus on the inverse problem and look at some of the challenges that we have in this field. So one of the main, probably the most significant challenges that we face is related to uncertainty. And the fact that we have very limited access due to the cost and technical difficulties associated with it. Subsurface description is inherently uncertain. And there are various degrees of uncertainty, various sources of uncertainty that come into the modeling process. There are also uncertainties associated with measurement, with modeling, and representing the physics. The second challenge that we have is related to in inverse problems is making sure that the solutions that we derive from our formulations are geologically realistic. So typically, subsurface systems are known to have multi-scale heterogeneity, and being able to preserve some characteristics of that formation that we deal with is an important part of an inverse problem. And also there are complex spatial patterns that we deal with that are typically not easy to describe mathematically, and at least in some environments. And these are two main challenges that we deal with in inverse problems. The other challenges, of course, there could be other challenges named, but these are some of the important ones that come to mind. Nonlinearity and computation. When we run these kind of flow simulations for realistic problems, we're dealing with very large scale simulation effort for even one simulation. Now, typically when we solve an inverse problem, we're dealing with probably tens and hundreds of simulations that need to be run either in an iterative form or in what we call an ensemble parallel form. And that needs to be accounted for, as well as the nonlinearity that exists in this system that can complicate the solution approach. And the topic of this presentation, mainly related to dimensionality reduction and the resolution aspect, is another challenge in inverse problems. And the main issue here is that even though we would like to have very high resolution representation, ideally, the fact is that for inverse problems, the data that we use in order to retrieve the properties that we are interested in are very low resolution. And that's an important part of formulating an inverse problem, knowing what kind of data will be integrated and what would be the information content in that data. So I will next begin my presentation on the dimensionality reduction aspect, keeping in mind that all the other challenges there need to somehow be accounted for when we solve inverse problems for subsurface flow systems. So why low-dimensional representation? As I said, one of the main challenges that we have is that the content of the data is very limited, but at the same time, there is geological properties or geological, physical flow-related properties of geological formation tend to have continuity in them, at least in the horizontal extent of them, and because of the way they are deposited. And that leads to a spatial correlation. And what you see on the right-hand side is a typical model showing the distribution of one of the flow properties. And the idea here is that because of the spatial correlation that is inherent to geological formations, we can come up with more compact representations that would try to keep the salient information in these models and sometimes get rid of some of the details in order to give us a low-dimensional representation that is more compatible with the type of data that we are going to integrate. And in this case, I'm showing there are various techniques for actually doing this kind of compact representation. A lot of people have worked in this area. The idea is very simple. We want to actually, instead of having pixel-based representation, we want to have a pattern-based representation, a representation that takes into account connectivity in the property field. And this goes back to a long time ago, starting with simple zonation approaches that people used in order to describe connectivity in this field, and all the way to what we will be discussing today and what people are working on in terms of using deep learning and machine learning techniques in order to actually do this in a more sophisticated way. So the approach that I'll be discussing is related to approximation theory and linear expansion. There are, of course, spatial techniques to do these kind of low-rank representations, but in this presentation, I will focus on a signal processing perspective on this, where we actually look at transform domain and compressive transforms to do this kind of representation. So the idea is, if you look at a representation of a parameter u, which is spatially distributed, as you see on the left-hand side here, we want to be able to actually have, so if you have a basis, mathematical basis to represent this could be a Cartesian coordinate system, we can have a full, basically complete representation of this with a bunch of coefficients and a basis function, set of basis function. Now, if you actually find a set of desirable basis function for compact representation, then we may be able to actually keep only a few terms. So you can look at this as a coordinate transformation, where you're trying to find new sets of coordinates that will give you compact representation. And that new set of coordinates is described by these basis images that you see, and the corresponding coefficients for each coordinate system are the v coefficients. Now, in pictures, what's really happening is that you're trying to have a representation of this three-dimensional model using these basis images and the coefficients in front of them. Now, the key question is, so this is one way to accomplish low-rank representation, where the idea here is that instead of n terms, or n pixels, you will end up with s terms, and those terms are the coefficients in front of each basis function. And this s is a small fraction of n. So that's basically the premise here. And the key question is now, how do you find these basis functions, and basically how do you formulate the problem from there? So looking at the inverse problem, this is a typical workflow that we follow. There's typically some data available, and what we do is we start with some initial model that we develop, and we use that model to do predictions, and we look at the mismatch between prediction and observations in an automated fashion, of course. And we look at that mismatch, and we want to try to update our model in order to minimize that mismatch, and hopefully the update should be in a geologically consistent way. And the idea here is that now, instead of a pixel-based representation, we have a low-dimensional representation. So instead of dealing with tens of thousands of parameters, we actually have a low-dimensional representation in the order of 20, 50, or 100, depending on the complexity of the problem. So that's really the gist of it. So that's what we want to accomplish. And there are very different types of techniques and different forms of basis function that I will briefly go through a few of them to basically show how this works. But before we move on, there are some key points. Anytime we talk about these type of problems, we want to develop a technique to solve inverse problem in subsurface flow system and have low-rank representation. I think these points are very critical to have in mind. Number one is that inverse problems are fundamentally different from image compression problems, in the sense that when we do image compression, we are given a known image, and the idea is just to compress it. So the image is known. In an inverse problem, the image is unknown. What we are looking for is an unknown to us. So that makes the two problems very different from each other. Typically, we are dealing with reconstructing an image from very limited and oftentimes non-linear dynamic data. Whereas in image compression, the idea there is how you can actually maintain a good resolution while having a low-rank representation. For us, the resolution is somewhat dominated by the data that we will be using. And then the second point is that the data is limited, which I mentioned that, and the content, quality, quantity, and resolution of the data are important things to keep in mind. What is it that we are going to use in order to reconstruct the images we are, or the properties that we are interested in? And we need to keep in mind what is doable and what is not doable. Another important issue was related to geological realism. So what we do, any solution we come up with, we work with geologists, and they are the ones who are expert and will tell us what makes, what is realistic, what is not realistic. So we need to kind of make sure that the geologists are also in the loop and are okay with the solutions that are generated. Typically, mathematical descriptions and constraints associated with geological plausibility are not very trivial, and that's one of the challenges we have to kind of deal with. And then we also have uncertainty about geology. On one hand, geological kind of information would help us to constrain the solution, but on the other hand, we also know geologists have their own uncertainty. So we may not be able to have one interpretation of what the environment or the kind of patterns that they are trying to reconstruct, what they look like. There could be uncertainty about those. And then finally, always computational and technical resources. These days computation is cheap, but it's not unlimited. So whatever we do, it should be computationally feasible and practical. So with those characteristics in mind, let's review a few of the classical techniques and talk about some of the properties, pros and cons, until we get to some recent work. So Fourier bases are probably the most classical techniques in image processing, and they are very powerful, very strong theoretical backing. And the idea here is that these sine and cosines with different frequencies can provide functional representations for particular types of functions, in particular smooth functions. And there are image compression techniques that use these kind of sines and cosines in order to provide a low-rank representation. There are also, I'm naming discrete cosine transform, which is related to JPEG compression, and GCT, which is kind of a generalization of that that can be applied to irregular geometries and boundaries. So as I said, the Fourier basis has very good compression performance, but it also has its own downside. And in particular, the Gibbs phenomena is very popular. If you try to use various smooth sines and cosines to represent a discontinuous function, you will end up having some difficulty, at the points of discontinuity. So it's a very well-known phenomenon. How important that is for inverse problem in subsurface, I will briefly talk about that later. But in image compression, these are issues, those basically discontinuities appear in a lot of natural images, and it's important to deal with them. So here's an example showing two types of images. On the top, you see a channelized environment. At the bottom, you see more like a Gaussian distribution. And if you apply this Fourier type transform, you basically go to a different domain. And that domain, the Fourier domain, in this case, the DCT coefficients are shown in the middle. And you can see that once you transform the original image, when you go to the Fourier domain, there is no notion of space anymore. So you cannot really associate these coefficients with the space anymore. What you can associate them with the frequency numbers and basically the spectral content of the image. And typically, because larger scale correlations are involved, you can get away by truncating a lot of the coefficients that are related to the smaller scale features and have a low rank, relatively smooth representation of these images. Now, this is a compression problem. In an inverse problem, as I said, you're basically trying to identify these coefficients in order to match the data that you have in the field. And if you look at these type of basis functions, they have some orientation, kind of patterns in them, but they don't have anything related to geology in them. So these are non-geological basis functions. So there are advantages and disadvantages to any of these techniques. Fourier is not an exception. It has excellent compression and decorrelation power. Typically, we use that if there's no geological information. If you have geological information that can help us improve the efficiency or effectiveness of these basis functions, we would probably try to do that, having in mind that geology also comes with uncertainty. These are pre-constructed basis function computation, are very efficient, and a very well-established theory behind them. In terms of limitation, these are global basis function. It means that you cannot really adapt them at a local zone in the field. Resolution, it can be achieved either in frequency domain or in the space domain, but not both. There are windowed versions of this, but that's pretty much at that point you're moving to wavelets. And then the solution tends to be smooth, and geological interpretation could be an issue here because we're not using any geological information, and the solution may not have any geological features. Now, the next one on the list of image compression techniques is, or data-independent methods, is wavelet transform. For wavelets, basically they're considered the upgraded version of Fourier for natural images and image compression algorithms. These are the standards used in JPEG 2000. And the idea is these kind of wavelets are designed to give multi-resolution representation as well as a space and frequency localization, which is something that Fourier bases do not have. So adaptive localization and resolution in space and frequency is one of the key characteristics and advantages over Fourier. And this image is basically showing the space frequency tiling where you can have adaptive resolution for space and frequency. Typically, the way they work is there are two sets of filters, low-pass filters or scaling functions in these wavelet transforms that try to preserve features that have very low frequency and get rid of the details. And on the other hand, there are high-pass filters working with the low-pass filter, the corresponding low-pass filters, and their job is to detect higher frequencies and get rid of low-frequency information. So these two together these two sets of filters try to decompose the original signal into low-frequency component and high-frequency component and anything in between when they're done iteratively for different scales. Now, here's an example. It's a one-level decomposition example showing an original signal on the top left. And the low-pass filter will basically try to preserve the low-frequency information. And the high-pass filter, after doing the filtering, would actually get rid of the low frequencies and try to detect the high-frequency feature. So if you're doing image compression, this is a very powerful property to have, where you can actually look at some of the smaller scale details that our eyes are very sensitive to, and try to detect those and preserve that in your compression if they're important. So if we go to 2D and cascaded wavelets, where you actually have the first level, in the first level, you end up with this 2D image showing a channelized image. The first level, if you pass it through the low-pass filter, you get this upscaled version, and then the high-pass filter in different directions, and the diagonal, which means horizontal followed by vertical or vice versa, will give you the detailed coefficients. And then in the next level, you can perform this iteratively. In the next level, you can take the scaling coefficient and repeat this process. And that's what will give you level 2. And then you can basically repeat that to get level 3, level 4, etc. Right? So once you get to this level of decomposition, you actually have the lowest frequency showing up as your scaling coefficient. And then you can see that you have divided the other frequencies from relatively low to all the way to very high frequencies. And that gives you, and the key difference here is that now you actually, when you look at the transform coefficient, you see some information in space as well. So that's the space frequency resolution that these filters have. So just a comparison between Fourier and Wavelet, you can see that after transformation of the image, you can see there are traces of these edges of these channels. This is very typical from Wavelet because it the detail wavelets detail coefficient will try to actually detect this edge information or discontinuity information, whereas the Fourier transform or DCT doesn't do that. So how important that is, it's basically depends on the application. If you really have information to be able to detect those edges, in our case, we have dynamic data, but it's very unlikely for the type of flow data that we have to be sensitive to those edge information. So in terms of contribution of this feature to Fourier for low rank representation of flow problems, it really depends on the resolution of the data. But in image compression, definitely is an advantage to have. There are different types of wavelet, and this will be related to some of the things that I will talk about in convolutional neural networks later. And the idea with these wavelets is that they're pre-designed. So depending on what type of signal you want to process, there are actually wavelets designed with particular properties that you can select, or you can even design them yourself. Examples are sizelets for seismic data. But one thing about these wavelets is that they're not really trained by any data. So they can have a specific properties, but those are very generic, and they're not adapted to a particular type of data. And typically, we use the same type of wavelet at different scales. So that's another. So the same filter is being used for the image at different scales. So in terms of comparison between the two, I mentioned similarities in terms of excellent compression power, similar performance for high compression rate, which means then you're only interested in larger scale features. And the difference there is basically the localization aspect, as well as the multi-resolution aspect of the wavelets that are very important. But one key observation here is that for inverse problem, we may not be able to actually see that difference just because of the nature of these problems and the type of data that we have. If you have very high resolution data that for an inverse problem, then wavelet can actually show those kind of advantages. Now, there are also the second class of techniques in compressive transforms are techniques that are data-driven. In a sense, those basis functions are derived from data. So in the previous two cases, those are just pre-constructed Fourier and wavelet bases. Now we can actually, if you have prior information and data, just like the images shown in here, we could use that the classical technique with principal component analysis, or truncated SVD, in order to come up with low rank representation. There are also nonlinear versions of these, kernel PCA, where we apply kernel trick. It's one of the techniques used in machine learning also, in order to kind of deal with nonlinearity and some complexities in these images. We have also looked at sparsely construction as a recent approach, relatively recent approach in signal processing and image processing, where we looked at sparsely construction, both for Fourier and wavelet domains, and as well as constructing sparse dictionaries. And this is also a very active field of research, generating what they call dictionaries or generalized version of those bases that have a sparsity as a feature in them. And by sparsity, what it means is that instead of reducing the rank, let's say, to S, or let's say a number 20, we actually keep the search space or the dimensionality at a higher number, let's say in this case 2000, but then we know the signal is sparse. And there are actually very efficient techniques, recently developed techniques, in order to deal with these kind of signals where they are sparse, there is no ranking, just like PCA or SVD, and you need to kind of search that space in order to find the sparse structure that matches your data. And we have used this in some of our publications in the past in order to deal with inverse problem in subsurface. Now, with that, I'm going to now move on and talk about low-rank representation through deep learning and neural network architecture. So very briefly, I assume a lot of you are familiar with the basics of neural networks, trying to mimic the behavior of human brain and neurons. And the idea, if you want to simplify that, basically the idea is that putting together a network that can recognize, detect patterns in the data, and use that in order to do prediction. And there are various forms of this. I'll briefly mention a few important ones. So you can have fully connected networks with some hidden layers. We have input layer, output layers. And some of the basic elements are the weights that are associated with these connections, and the activation function for any node, as well as the output layer that is basically either a label, or depending on whether you're doing classification or regression problems. So we put together this network. The weights that we see in here are the main unknowns in this network, and we use data in order to train those weights. So this network can extract the salient patterns in the data and use those in order to do prediction for us. Now, a very important family in this class of techniques is convolutional neural network, or CNN, where you bring convolution in order to actually achieve a few important properties. One is that for images, convolution operation is a very efficient way of extracting local patterns and local features. And that would also allow, for high-dimensional problems, bringing convolution can result in significantly reducing the number of parameters compared to fully connected network. So we have this convolution operation, similar things we did in wavelets and filter banks, except that here we have a lot more filters. It's not just one type of filter. And those filters are not pre-designed. Those filters are actually learned during the training process. These convolutions are passed into the next step in each layer, where we do downsampling. We do activation first. Typically, we can introduce some degree of nonlinearity through the activation function that we introduce for each node. And from there, we actually can do some pooling operation, which is pretty much some subsampling. Similar operation is actually done with wavelets too, just basically replacing multiple pixels with a single pixel that carries the most important information of those. And this results in reduced dimensionality and redundancy in these weights. And then we put together the architecture in a supervised learning framework and try to identify the weights associated with the convolutional filters. Here's a typical architecture. Each layer involves a convolution layer, a activation layer. In this case, ReLU is a very popular one, and then the pooling layer. And then the results of each layer is passed on to the next layer, and then you design this architecture, and you provide some input data and output data to solve either regression problem, classification problem, so you can formulate those problems using this type of architecture. Now, some important observations: the weights in these filters are the unknowns to be trained and learned, and those weights actually try to detect important patterns in the data, in the input images. So we use many filters per layer, and that means we can detect a lot of diverse features, and multiple layers with subsampling is used, and that can lead to multi-scale feature detections. And fewer parameters compared, as I said, compared to fully connected network, and typically a smaller size filter are sufficient to detect local patterns. So I'll just quickly move on. So now, how do we use that for dimension reduction? So typical, the classical or popular approach is autoencoders. Autoencoders are architectures in which you actually start by an input into a network, and that input gets typically sequentially reduced in terms of dimensionality to a lower dimensional layers. And in the center of an autoencoder, you have the lowest dimension typically, and that is what is referred to as the latent space. And that is where you can actually go from the original parameters X to the latent variable Z with much lower dimensionality. And then this part is the encoder, where you actually map a high dimensional input into a low dimensional parameter. And the right-hand side is the decoder, where you go back, you do the opposite, you go back from a low dimension to a higher dimension. Once you actually do this kind of training, the output of this autoencoder is an approximated version of the input. And the idea here is that once you're done with this, you can take the decoder, and the decoder, you can start with a low-dimensional parameter and put it as an input, and it would produce an approximated image in high dimension. An important class there is the convolutional autoencoders, where it's very similar. Instead of fully connected neural network, you use convolutional neural networks, similar to what we had with convolution, the same properties there. But an important class here is variational autoencoder. The idea here is that you can actually do a stochastic mapping between distributional information in the data space and the latent space. So you have the encoder representing a mapping, a stochastic mapping from the original data distribution to the low-dimensional latent distribution. And the decoder doing the opposite of that. The key here is now you can actually specify very simple distribution in the latent space, like Gaussian, standard Gaussian, uncorrelated Gaussian distribution, and try to learn the weights of these networks such that those simple distribution can map into the original complex data distribution that you have. So we have used some of these, and others have, of course, used these techniques in subsurface flow inverse problems for parametrization. Now, I'm showing some results in this case using a single geological kind of scenario and multiple geological scenario to account for the uncertainty that we can have in some aspects of the geological information we have. In here, we're basically looking at a 5-spot pattern, two-phase flow, and these are the solutions coming from principal component analysis and VAE. What we are seeing is that the VAE performed, and these are the iterations that are used in order to find the solution from an initial guess. What we will see is that the VAE, if designed properly, can actually easily outperform PCA. PCA is a very kind of a simple version of the autoencoders, a special case of it. Now, if you go to multiple scenarios, that's where you really see the advantage of these convolutional neural networks, just because of the capacity they have in order to learn very diverse features. The other aspect is the generative power of these kind of architectures like VAE, and there's also adversarial models where GAN models, where you can actually generate very complex features, spatial patterns from low-dimensional simple distributions. And if you look at this VAE comparison for generating these type of complex channels and compare it to PCA, PCA doesn't have that much of power for generating models. Another aspect is nonlinearity that is introduced in this kind of network, and you can see as we add more layers and more within each layer, we have activation and max pooling, and these are nonlinear operations, and that can add to the nonlinearity in the architecture. You can see that as we increase the number of layers in our architecture, we get cleaner and cleaner, basically, image representation for these kind of patterns. One other important aspect I briefly mentioned was related to redundancy and capacity of the convolutional neural networks, is that the ability to actually absorb or to represent very diverse patterns, learn them and represent them, take advantage of them for prediction is an important property that that we have compared to PCA and other techniques, and we see a key advantage there. So my last topic, very briefly, is that if now that we are dealing with the autoencoders, we might actually, instead of actually doing row rank representation for parametrization, we can actually do row rank mapping. So the idea here is that if we can do low rank representation in the model space for geological models, and low rank representation in the data space, which can be easily achieved, then we might as well connect the two and develop architectures that can actually give us mapping in the low dimensional subspaces or manifolds that we design through these architectures. So in fact, people have been looking at latent space representation for proxy model development, where you actually try to replace the original forward simulation with a low rank or latent space representation to go from the model to predictions to data prediction through a proxy model using these kind of architectures. And then the beauty of this is that you can actually design the inverse mapping too directly. So you can actually, and we had a recent paper on this, you can actually go from the data to generate a direct mapping from the data into the model space and generate model. Of course, you have to do training for this, and that involves having some models to do, having some models with the corresponding responses, which means you have to run the reservoir simulation to get those kind of data for training. And once you train that, and if everything goes well, you would be able to actually provide your observed data in the field and look at what kind of models are generated from the trained network. And here's an example taken from a recent paper that we had in which we actually implemented something similar to what I explained. And what you see is basically a reference case on the top for prosody distribution and what the network was able to generate, the similar type of architecture. So that's pretty much all I have. I just present my concluding remarks here and open the floor for discussion. Main conclusions here: flow properties exhibit strong spatial correlations, and they're amenable to low rank representation. That's the key property that we know about the type of problems we deal with. Classical image compression methods are useful when geological information is not available or highly uncertain that you cannot trust it. But data-driven methods, on the other hand, can provide very effective low-rank representation through training. And they can be, they are customized, and as a result, what that means is that they are also sensitive to the quality of the input or training data. And deep learning provides generalized low-rank representation and promises to hold some potential for addressing some of the challenges we face in this area. And subsurface flow inverse problems, I highlighted that because it's a very important problem or aspect to keep in mind, are fundamentally different from image compression. So a lot of the techniques that we see that are developed in either image processing, approximation theory, or applied math in general, most of them are designed to approximate a known image and somehow retain some of the important details of those images. That may not be what we are interested in an inverse problem related to subsurface. Those details, we may not have information to retrieve them when we go to an inverse problem. I think that's a very important consideration to have in mind. And with that, I'll end my presentation. I thank you for your attention.
Thank you very much, Behnam, for this very inspiring and very informative talk. We really enjoyed, and also I didn't notice that you actually passed quite well through the time limit, but the story was so engaging that we just didn't notice. So thank you very much. Without any further ado, I would like to give the floor to Kamal to chair the discussion.
Thank you, Hadi, and thank you, Behnam, for this fantastic and thought-provoking talk. I actually learned quite a lot of things about low-rank representation. We have a few questions from our audience. I'll start with Sarah Behbani. She's put two comments. The first one she's saying is it's a cool idea. Can we couple this method? I think she was talking about wavelet transform with the multi-scale reservoir simulation approach.
Okay, I talked about a few ideas. Number one, I have to admit, my area of research is not reservoir simulation. So I think experts in that area probably have looked into these kind of low-rank representation. I know some of these ideas are used, both in, I know in particular for proxy model development. Now, whether they are used in reservoir simulation directly, that's something I wouldn't know. These are very generic techniques. I think a lot of people right now are looking at taking advantage of machine learning and deep learning, but I'm not sure these low-rank representations are very different techniques. Which one she's referring to? But I would be surprised if they haven't looked into it or they're not looking into these kind of ideas for reservoir simulation. Proxy model for sure is one of the main applications here.
Thank you. And now, sorry, my daughter invaded my room. I think she was shouting behind. So we have got three comments from Arthur. although one of the audience has already tried to answer something, I think I would like to have your views on it. So he says, my question is if it's possible to perform a local low rank instead of finding it as global ones, and if you can briefly mention the most favorable approach for locally found low rank systems, especially challenges, pros and cons.
Yeah, one of the things I mentioned was related, the difference between Fourier and Wavelet is exactly that. Localization that Fourier offers in a space and frequency. What that means is that you can actually be in frequency domain and actually have information about the space and where these features are. Or you can be in the space and actually have some information about the frequency. What that allows you to do is selectively choose which region. So if I go back to one of the slides that I showed, I guess here. So if you look at the difference between these two images, you clearly see that where you have these information about the channels, you have those coefficients related to the edge information. Now, you could obviously focus in a specific region. Let's say for us, we are dealing with data from wells, which means that we have a little bit more confidence about the neighborhoods around the well than far away from the well. So if you want to localize it around the well, have a higher resolution parameterization around the well compared to far away, then you could actually look at keeping more coefficients in those regions. You can do that. Similar ideas have been actually developed in multi-resolution parameterization in the space domain, which is you basically adaptively coarsen or refine your model as you go through the inverse problem, depending on what the data sensitivity is telling you. Now, when it comes to the deep learning, there you could also set up a multi-scale architecture. In fact, for spatial images, naturally these kind of techniques that in different layers, different filters detect different scale of information. If the idea is to have a multi-resolution representation, architecture should be available already, if you look at the literature, to actually take advantage of the multi-resolution aspect of these models.
There was another comment from Arthur as well, like how sensitive the locally based approach would be with respect to the local domain size.
How sensitive
the locally based approach, or
I'm not sure if
I think what I can interpret what he means. Perhaps he means that you can localize or cut it in different ways, and then in the space domain, from what I
so you can achieve those automatically. Which again, I think the first thing is whether you want to use data or not, meaning geological data or not. I distinguish the two approaches, and I don't think they should be even compared against each other, just because it's apple and orange. In one case, you don't have geologic information, but you want to do low rank representation, you go to classical image compression techniques. In the other case, you have some geological information, of course, with some uncertainty, then you go to data-driven if you trust the data, and if you can incorporate some aspects of the uncertainty. Now, if you go to the classical techniques, the wavelet approach would allow you to do that, which means that you would be able to actually generate different sizes of local features or pixels, if you wish, by actually taking information from different scales that I showed in the wavelet coefficient domain, and depending on what scale you're interested in, you go to that scale and try to maintain some of the coefficients for the regions you're interested in. That's for the case where you don't have geologic information. If you have geological information, the classical technique like PCA, SVD, they're not localized, and they're global. And you may be able to design localized feature. It means that you have to actually do the localization to generate training data yourself, and then do the parameterization with that. Now, when we go to deep learning, again, there are architectures there that would allow you to generate multi-scale representations.
Thank you for the explanation, and thank you, Hadi, for helping out here. There's another very related question from Musa Hossein Emer. So, do you think that usage of deep learning can help us provide a more deterministic image of local fractures and fault patterns from the seismic data?
All right. So I know that deep learning has been used in seismic literature. Even more sophisticated versions like GAN, generative adversarial networks, that have been used. For seismic, there could be some promise there, just because the amount of information is very different than what we deal with in an inverse problem with dynamic data. The flow data, unfortunately, is basically giving you some lumped response. So it's not really localized. With seismic, the story could be different. It all depends. So if the question is that, can we actually represent smaller scale features like fractures in our images using these kind of techniques? The answer is yes. I think the more important question is that when you go to an inverse problem, do you have sensitivity to those details? Can you actually capture those from your data or not? Let me actually mention another aspect of this, is that some people have tried to do this, where they actually look at the resolution as you can have a resolution for your inverse problem, and you can have a higher resolution for with some stochastic component to capture uncertainty. So people have looked at some of those fine scale details to be added to your solution in order to represent the fact that you lost that information, and you use that for uncertainty quantification. So just because I say those details cannot be detected, it doesn't mean that we completely forget about them. It just means that the data is not sensitive to that. So you just need to keep that in mind.
Okay, thank you. There's a question from Rasul Sufi. Nice talk. He said, thanks. Would it be possible to predict any type of distributions for properties of field by inverse method, or just simple discretized one?
Let's see. To predict any type of distribution for properties of field by inverse method, or just discretized one? Oh, by discretized one, if you mean the channel facies, if that's what you mean by discretized, not really. There's no limitation. In fact, from an inverse problem or from a mathematical description, those are more challenging. The discrete versions are more challenging, and people have tried ideas of kind of making sure the solution is discrete or remains discrete. But if the solution is not discrete, you're good to go, because it's more difficult to actually preserve discreteness. And the key also aspect to keep in mind is discreteness is not really the fundamental property we should be after. I think discreteness, less facies, yes, we categorize them and they are discrete. But that doesn't mean what exists there is really discrete, number one. And number two is that what is really most important is the patterns, detecting the patterns. And if you lose some information on the edges, right, meaning that if you smooth out some of the edge information, or if instead of a discrete solution, you come up with a continuous solution, as long as the pattern is detected, I think that's really where the focus should be. The connectivity pattern is detected. I don't want to minimize the effect of boundaries and edges. They can actually have important effects on the flow pattern. But from an inverse modeling perspective, those, we may not have data to actually constrain the model, the edge information. Now, if you want to preserve that, you could by making sure the solution becomes discrete. There are techniques to do that. But from my point of view, it's really the connectivity that we should look for, not the detail kind of discrete or versus continuous.
Yeah, thank you for the explanation. The next question is from Masood Shizwan. Well, thanks for this interesting talk. He asked, supervised learning, how did you acquire enough labeled data for
Yeah,
training?
that's a great question, and I think with machine learning being so popular these days, we may lose sight of that question, which is data itself. I think the main ingredient in here is data. As the name suggests, it's data driven, right? So the data, typically, these kind of techniques come out of applications in which data was cheap, data readily available, models did not exist, or were too complex to build, right? Those are the idea. Now, when you come to our application, we are heavily physics oriented, right? We have a long history of developing physics-based simulation. In these kind of applications that developing proxy models, doing inverse problems, the data comes from simulation typically, because the physical system, we really don't have enough data from the physical system to be able to do this kind of training. So I think that's an important thing to keep in mind, that the data could be computationally expensive. The training itself is expensive computationally, but acquiring or generating the data is another computational aspect. The answer to the question is that these are simulated data. They're generated from simulation. The idea here is that you do these kind of mapping offline based on simulated data, and then you bring your trained network online and very quickly do your predictions or inversion, whatever it is you're trying to do.
Okay, thank you. Hadi, do we have time for more questions?
Questions are very interesting now when we are going even down. Pick, please, 2 or so more questions, because we have him now here and it will be recorded and for many years to come and be used to. If Behnam, you're okay, we can continue 2-3 more minutes.
Sure.
Please.
Okay, so there's a question from Oleg Iliev. So it's a nice talk. Few words about area of applicability. For example, PCA, Kolmogorov and width indicates if low rank approximation is possible. Are there anything similar for DL?
And width indicates if low rank approximation is possible. Are there any similar for? There may be. I'm not familiar with any indicators in terms of whether low rank representation is possible. It really depends on the type of data that you have also. I'm not sure if there's any theoretical kind of framework to show that. But for natural images, coming out of our own application, for natural images, the underlying, if there was no correlation, no patterns in those images, there will probably be no image processing or no signal processing. We heavily rely on the correlation in natural images. When we come to geology, I basically mentioned that the continuity in this depositional environment, we have local discontinuities for sure. We have deformations, we have faults, and we have fracture. All of those are, valid, sources of discontinuity. But locally, if it's not heavily fractured medium, locally you can assume there is some continuity, and that's really what these techniques are very good at, detecting those and exploiting them.
Okay, I've got 3 very quick questions. They are all interesting. I'll go for Kishore Kumar. How do you ensure that the data is not overfit when you use CNN?
Yeah, I didn't really go through all the details here. I think that whenever we do these things, if you ever done these things, you generally divide your data into training data, validation data, and test data. That's basically a practical approach, just to make sure when you're training, there are some unseen samples, and you're monitoring the performance for those as well. Of course, you don't want these type of networks to be memorizing your input-output, because that's not the idea. You want to generalize beyond that. And that's why we keep some of the data for validation, to make sure the similar type of performance that we see in our training data, we also see in our validation data. And that's during training. Before you stop the training, you actually compare the performance for seen and unseen data by the network. And that's one way to assure. But there are signs, the thing about, unlike the image processing techniques, or classical image processing techniques, when you deal with neural network architecture, there's some level of tuning, there's some level of trial and error. There is no, a specific rule of thumb. There could be a few here and there, but nobody will tell you go exactly design this network with these many layers, these are the type of filter you should use, dimensionalities, etc. There's a lot of trial and error involved.
Okay, thank you. So there's another question from Jebuhura. Wonderful talk. How to determine the size of the latent space in autoencoders?
Yeah, that's exactly what I was saying now. It's very hard to have a specific even rule for that. Typically what you do is you go through sensitivity analysis. You look at different number of different dimensionalities, and you, of course, with experience, you learn a lot. So with experience, instead of trying 100 times, you probably try 5 times. But even then, you have to actually try different dimensionalities and see what dimension would be more appropriate for the kind of problem that you're dealing with.
Okay, I think we can finish the question answer session here. But if somebody has any question, please feel free to send email to Behnam. I'll pass it over to Hadi now. Thank you, Behnam, once again.
Okay.
Thank you very much. Thanks, Kamal. Thanks, Behnam, and the audience for the wonderful discussion session. I believe there will be many more, but Behnam has an email address. I believe he checks his email address as much as he can. So please do feel free to contact him and reach him directly. I would like to just take the chance and introduce our next week speaker. Our next week guest keynote speaker is Professor Miles Allen from University of Oxford. Miles will speak about achieving net zero by decarbonizing fossil fuels. So until next week, the same time, stay happy, healthy, and safe and sound. And we see you all next week, the same time. Behnam, thanks once more. And it was really a nice and informative talk.
Thank you.
Thank you, Behnam.
Bye-bye.
Bye-bye.